from the wrestles you've been having with waves and such?
It's been very good. I just thought that I haven't really gotten to a good enough standard with waves so far. I kind of
Okay.
like to get a good understanding of it.
Did you just start the topic, or whereabouts are you with the topic? Have you finished?
No, I think we're kind of mid. Where are we? I think we actually sort of we finished the topic. We finished the topic. I just feel like I should get just a better understanding of it because the first time doing it.
Okay.
A bit challenging.
So you've actually finished the topic.
Yeah.
Oh, you guys are cruising. You guys are absolutely cruising. Okay. And have you had any assessments on the topic itself?
No, not yet.
And do you know when that may be scheduled for, just to kind of see what time we've got to play with and how deep down the rabbit hole we can go?
Yeah, I think I can find out. There's a physics 1 and a physics 2.
Okay, cool.
I don't know which one has.
Which one is going to contain the waves topic, but you know that you're going to have 2 assessments. Doesn't matter. When you go to school, you can always check with your teachers and then get it more concretized, if there's such a word. Okay, cool. So let me just put here waves then, and just to kind of
far away.
But it's not far away, right? Okay. Do you reckon?
Oh wait, no, it is far. It's
Okay.
maybe like a month or so.
Gives us a little bit of time. When are you guys starting end of year exams?
The 16th.
16th of May. Okay.
Yeah, and then I have physics on the 20th.
Oh, that's good. Okay. So physics
and then
itself.
Another one in the 16th of, I don't know how much, April, May, June.
Oh, and then you've got another one on the 5th of June.
On the 16th of June.
Wow. Hang on. So you're starting in May, 16th May. That's a long time for exams.
It's a spread over 5 weeks.
Oh, that makes sense. I was going to say
I can send you the timetable if you want to look at it.
Do that, just so at least I know as well, and I'm in the know. Okay, cool.
Yeah.
All right. So waves, just as a general conversation now, which arenas did you really think, I have no understanding on what's going on? I'm sure you're going to have a few pockets, and then we're going to try and find some foundation to try and give you the basis of how to get your head around those.
I definitely thought the young double slit experiment.
Yeah, I'm going to put those. Those are pretty confusing. I hear you there.
Diffraction grating
double
and
slit.
Polarization are the main ones that I just feel like I should get a better understanding of.
Okay, polarization.
I would not know.
And the diffraction grating. Okay, excellent. Okay, so young double slit polarization. So this is more like on the waves part 2, more or less on the advanced wave side as opposed to the basic waves. Good, that's not a problem.
Yeah.
These are generally a bit tricky for a lot of students to grapple their head around a little bit. But I mean, once you kind of understand what's going on, it's a little bit easier to appreciate, okay? But in addition to these, there are elements from waves part 1, if you like, that feed into these. So depending on how well you understood those core concepts, if you didn't quite get them right, it could mean that these then therefore become almost near impossible to really get the full gist of what's going on. So what I'll try and do, just for my own diagnostics, not that I don't trust what you've told me that these are the main areas, but it's just standard procedure. I need to prove for myself that these are indeed the only areas that we need to tackle, okay?
I mean, I would agree. They're probably more. These are the main ones.
Yeah, and
Yeah.
and that's fine. That's fine. I will make these my primary focus, but I also want to ensure that if there are any other gaps in other areas, we equally patch those up as well. All right, super
Yeah.
duper. So what I'll do, just as a little bit of a diagnostic, we might just have a run through a couple of questions here and there, and then just see how well you've understood. So we're just going to look at, let me just insert a page here, blank page, after current. Okay, so basic, so this is just we're going to call it diagnostics. Let's call it that. Right, so let's imagine we're just going to start off with this nice basic sinusoid wave. We'll draw a couple of them here, and we'll draw another one that side, like so. Here's my wave, and likewise another one. Right, so here we have, just going to put displacement. I'm not going to write the full thing, meters. Likewise, displacement in meters. We've got time, seconds. We've got distance in meters. Basics, these are what we're going for. What does that position represent from crest to crest?
No wavelength.
Cool. Wavelength, spot on. And what does that represent?
The period, or the time period.
Good, the time period, okay? So you are aware that whenever you're trying to work out what these are, you need to look at what's on this axis. Yeah?
Yeah.
So also good. Excellent. So let's just look and analyze this. So this is showing the displacement of a particle with time. So then if I asked you and I said, just a true or false question. Yeah, so we're just going to call this wave A, and we're going to say wave A represents a transverse wave. True or false?
I would say true.
You'd say true. It's actually false.
Oh, is it? Oh gosh,
Yeah.
oh, I definitely do need to.
Not to worry, because this could be false. The reason why I say it's false is it could be longitudinal.
Yeah.
Or transverse. Why? Because we're not told how the particle is moving with regards to the direction of the wave. We're just being told how the particle moves with time.
Yeah.
Okay, so even in a longitudinal wave, what happens is the particles oscillate. Anytime we have an oscillation, a to or from motion, that is a periodic motion, and the periodic motion is normally represented by a sinusoid. So it could be a longitudinal or transverse. So this here, the answer would be false for that. Okay, so just something to be mindful of. Good. So we know, of course, about the oscillations, and I know why you picked transverses, because you obviously know about the direction of the oscillations with regards to the direction of wave travel. So no problems there. The next thing we are going to try and look at perhaps is something to do with also phase. Yeah. How are you with phase difference? Because that links into Young's double slit and elements of diffraction in sort of understanding it. Okay.
Yeah.
Go on. And I'll give you a little bit of an insight. Young's double slit can be pretty complex. I'm not going to mince my words there. But the beauty of what I've got is that I've got some simulations which will bring to life what I say. So then you can fully understand, and we can play around with it, and you can see what it's all about. And unfortunately, it's not a simulation you can find online. Yeah, so it's on my system, and it's just one of those things. I wish I could have directed you and said you can find it online, but it's one simulation I had from many moons ago, nearly 20 years, when I was doing my A levels, and I kept it.
Wow.
I know, that's what I'm saying. It's no longer there, but it's brilliant. I don't know why they stopped it, but I kept it because I knew it's a very good resource to keep. Right, so phase difference. Tell me a little bit about what you know about phase. Let's insert a new page.
It can be measured in degrees and radians.
Good.
It's a full wave has 360 degrees.
Okay, so very good. So phase difference. So we said it's a measure of, is one way you can say of how far one point is from another. Yeah, from another. In either, you said, degrees or radians. Any of these can be used. So if I have one wave, it's nice and straightforward with this definition, because all you've got to think about is, you've just got to think about it as a sine wave, haven't you? And therefore, you know that if this was a sine wave, you recall from your GCSE days that this would be 0 degrees, that would be 180 degrees, and this would be 360 degrees. Yeah. So if I, for example, had two imaginary points, which one point A there and another point B here, would simply be looking at this angle between them and would say that's 90 degrees. So what are these values now in radians? 0, 180, well, 0 is 0, so nice and easy. What's 180 in radians?
Pi.
That is indeed pi, correct. And this here would therefore be 2 pi, wouldn't it? Absolutely right. So no problems there. Okay, so this is for the phase difference between 2 points on the same wave. Sometimes we also introduce the concept of phase difference when we have two waves, in which case this definition is not quite the definition we use when we are looking at two waves. Okay, very similar idea, but just slightly different way of looking at the problem. So if I had, for instance, here, now we've got two different waves. Here's my first wave. That's not well drawn, but there we go. Something like this. And we had another wave, which I'm going to draw in green. And I'll try and make this start from, say it starts from there. I'm just going to make it nice and easy. So now we have two waves, wave A and wave B. Now, what is the phase difference between those two waves? What would you say?
90 degrees.
Correct. Okay, you're absolutely spot on. Now, it's easy in this case because, or another way to look at this is, how much would I need to shift one if I kept the other stationary so that the two waves overlap? Okay, and you're absolutely right. If you move this 90 degrees to the forward or backwards, it will match up in terms of the points here and where it cuts the axis and such. So in this case, for phase difference, for us to be able to find the phase difference between two waves, there's a condition that has to be met. What is the primary condition if I'm going to find the phase difference between two waves? What do you reckon that condition would be?
Do they have to be coherent?
They have to be coherent. And you've used a very, very good word there. Yes. So we're saying that wave sources, super stuff, we like scientific words, wave sources are coherent. Now tell me, what does that mean?
That means that they're sort of the same frequency or the same amplitude. I can't remember.
Now, nearly there. And this one they like throwing in for a few marks. So you definitely don't want to throw these marks in there. So essentially what this is has, you're not too far from the truth there. So when we talk about coherent, we're talking about a constant phase difference. Now, don't say zero phase difference, okay? Because that is inaccurate. So coherent means that they have a constant, that's a very important word, phase difference, and the same frequency. Very good. So the frequency has to be the same. Constant phase difference and the same frequency. Excellent. Okay, so no problems there. You've got the necessary foundation to start delving into more complex aspects of waves as well. Now, there's a formula you can use as well. Now, I haven't labeled stuff on this axis. Now, on this axis could it easily have been time, or what else could I have had instead of time? I could have had distance. Now, I made this very easy. Sometimes they do create complex waveforms. Now, if this was time, yeah, all you ask yourself is, you look at, so imagine this, the axis was time, yeah? Now, I know these are slightly easier to read because I aligned that one with 90 degrees, so that's slightly easier. But sometimes you may have some odd values in terms of phase difference where it's not so obvious. How would you then go about finding the phase difference between two waves if you were given an axis that was labeled in time? What might you do?
Could you find two of the same points on different waves?
Good.
And then see what time they're at.
Yeah. And then what would you do with that? Keep going. You're doing good.
Could you perhaps subtract or
let's imagine that we had time here. And I think just to make it easy, it's better if we try and add a few things here. So you said I need to find the corresponding point. So do we agree then that this here and this here are corresponding points?
Yeah.
We're happy with that. So what do I do with this? Let's call this, let's just call the interval here between these two, because we're talking in time. Let's call it a small change in time. Let's call it delta t. What would I do with delta t now if I wanted to find the phase difference?
Could you do, I don't know.
Not to worry. All we're going to do now here is we're going to be expressing things as a fraction. So because they have got a constant phase difference, they're going to have the same time period. Yeah, or in other words, because they have the same frequency, they're going to have the same time period. Why? Because we know that the relationship frequency is 1/t. So if they have the same frequency, they've got to have the same time period. Okay. Now this little equation here is probably, if not the most important equation in physics, it's definitely in the top 3 most important equations in physics. Remove this from the physics books and the whole world collapses. Okay, it's that drastic. Seriously, it's a very simple little equation, but it's so important. Okay, so F equals 1/t, as easy as it is super important. So here, if I wanted to find the phase difference, which we normally denote with the symbol phi, Greek letter, that would be given by, well, what is the fraction of this time difference as a fraction of the time period? And then would use that fraction and multiply it by 360. So then we would say, what is the fraction of this interval expressed as a fraction in terms of the time period? Now, note, of course, here that if we are in time, then the time period, as you rightly said when we started the lesson, that would represent the time period. So delta t over t multiplied by 360 would give you the phase difference in degrees. And if you wanted it in radians, of course, you would simply change that 360, if you want the answer to be in radians, to 2 pi standard. No problemos here. Likewise now, if now this was not in time, but expressed in terms of distance, then this interval now cannot be called delta t, it's going to be called delta x. So to find the phase difference, it's the same drill, but now you're going to say delta x over, now the time period is now going to be replaced by what?
The distance.
Yeah, but what is that now time period? Because now this
the wavelength.
Correct, thank you so much. And we'll do the same and multiply that by, well, 2 pi if we wanted our answer in rads or radians, and 360 if we want it in degrees. So far, so good.
Yeah.
Excellent. Okay, so these are the sort of main basics. You've got the foundation that we need. Now, of these, we can get a quick win by looking at polarization. Quick win. That one we can quickly tackle that one before we really go into the nitty-gritty of the other stuff. So let's just think about, let's insert a page here, blank page after current, and talk about this phenomenon of polarization. What kind of waves can be polarized? Let's try and address that first.
Transverse waves.
Yeah. Can longitudinal, why can't longitudinal then be polarized?
Why can't longitudinal? Because do they exist? They don't. Is it because they don't exist in like separate sort of planes? I don't know how to put it.
Yeah, I know. I'm getting your full gist there.
Yeah, I kind of hope being clear.
Yeah, but I absolutely. So in other words, no, you're right. No, I know exactly. I've absolutely got your gist of what you're trying to say. And I think if you're in an exam, you would try to think as, how can I phrase this a little bit better? But that is a standard exam question. Yeah. Why can longitudinal waves not be polarized? So this is worth knowing and being on the ready to respond to something like that. So in other words, when we talk about longitudinal waves, oscillate, or rather, let's put it this way, just to think about it. So longitudinal waves do not have a plane of oscillation. Now, what I mean by this is that we don't have an orientation where the particles are oscillating. Particles move to and fro, and that to and fro is parallel to the direction that the wave is propagating. So there's no such thing as a plane through which the particles are oscillating. On the other hand, transverse waves, okay? Transverse waves oscillate particles perpendicular to the direction of wave propagation. And so have a plane in which they oscillate, in which they oscillate. So what is this whole idea of polarization all about when we talk about polarization? So when we talk about polarization, it is the confinement of a transverse wave into one plane of oscillation. Okay, that's the one key thing here. So polarization is the confinement of the oscillations in one geometric plane. For this reason, it's okay, I'll just say it is therefore known as plane polarization. Super. Did you get a chance to play with Polaroids when you were learning about waves?
No, I don't think so.
Oh, that's a bit of a shame, because that would have definitely helped you understand it, but I can see why. No problem. We will still look at this. So if I have a blank page after current, there's a bit of a nuance in here that when it comes to polarization, there's one little piece of, there's a bit of a nugget, I'll tell you, that not many teachers know about, not many physics teachers, even those teachers who have been teaching for 30, 40 years. I've had conversations with them and they just go, wow, I can't believe I taught my students in the last 30, 40 years the wrong thing. Okay, so I want to make sure I address that, because if your teacher knows it, sweet. But I know that it's a minority of them. We're going to deal into that because that is part of knowing about polarization. Right. So let's just think of light coming from the sun, or any incandescent source, a filament bulb. Yes.
Yeah.
What type of wave is that?
Oh wait, I just realized. I think are you talking about those two filters that if you cross them over,
Yeah.
Okay, yeah. For some reason, I completely forgot about that, and I just realized.
Oh, good, because I was going to say you better go and ask for your money back. All right, good.
Yeah, sorry, I completely forgot about
chips,
that.
and I was thinking, surely, I'm thinking here.
Yeah,
the teacher would have just brought those in, like, because they're cheapest.
Exactly. Yeah.
Excellent, super relieved. So, where are we at now? Polarization, yes, because you've seen the Polaroids. Okay, great. So, tell me a little bit about the nature of light from, say, the sun.
It travels in all directions.
Okay. So travels in all directions. Good. Anything else? So if this is my source, what do you mean by that? So if this is my sun, for example, he's simply saying that I have
every single plane.
Yeah. Okay. In all directions, radially, so to speak, isn't it? Because it would be spreading out radially. And of course, we've got that intensity, power over area, and all that kind of stuff. Yep. Good.
Is it progressive?
It's a progressive wave. Yeah. Okay. So try and give me as many facts as you can think of. Progressive wave.
There's some people say
wave. What does the word progressive wave mean? In that it transfers energy and information. Anything else it transfers?
Heat. Well, that's heat
that's
energy.
Under energy.
What else does it transfer? Could you say photons?
Yes. Now you've done wave particle duality, so we can think about light can either be thought of as a particle or a wave. So you're right. If you want to think about it as photons, that's okay for now. So if you're going to think about light as a photon, then what does it transfer? So it's a good thing you've kind of mentioned that. So what would a photon carry? Yes, we know a photon carries energy given by the formula E equals hf. But what else does a photon carry? Apart from energy.
From energy, light's energy, and heat. It doesn't carry any mass.
There's no mass, no.
There's no mass. Could you say no, that's I don't know. I don't know.
That is a bit hard. Have you heard of something known as de Broglie wavelength? No, that's okay.
No.
All right. No, you will learn about it. Doesn't matter. You will learn about it. But the key thing is, right, when you learn about something known as wave particle duality, you're going to learn that something that is a wave can behave as a particle under certain circumstances, and something that is a particle can behave as a wave under certain circumstances. So we can be waves as well. We are waves, or we behave like waves under certain circumstances, and particles under certain circumstances. Now, anytime you have a particle moving, or anytime you have a particle transferring energy, if it is a particle, generally, then you're going to associate that particle with having momentum. Okay, so waves of these progressive waves also carry momentum. Please remember that. Now, you spoke about photons, and just as a bit of an aside, but interesting point, the new type of spacecraft that's being created will be powered by the momentum of photons.
Wow.
Yes. So when you've got a rocket, the reason why the rocket is leaving Earth, say this is fired by gas, is because there's a change of momentum, isn't it? The gases are firing off this way, acting on the rocket, but the rocket is also pushing on the gases, and so it moves upwards. A similar concept will be deployed, but using a spacecraft that has a cell that works off photons. Yeah, so that's something there. And the reason why they can do that is because photons have momentum. Anyway, that was just a little bit of an aside to say this is what's kind of going on the wider side of things. So please do remember that they have momentum, because if they have so much momentum that we, like the scientific community believes that it will be able to, power a spacecraft. And the idea of that is that then you don't need to refuel it. Okay. Anything else? So it travels in all directions. It's a progressive wave, carries energy, information, and momentum. Anything else you can tell me about light?
It can be polarized.
It can be polarized. You're right. Well, it is unpolarized at the source.
Yeah, it's unpolarized at the source.
Absolutely right. So unpolarized. You're right. And the other key thing here is that, very importantly, it is an EM wave. What do I mean by EM wave?
Electromagnetic.
Electromagnetic wave. So guess what my next question is going to be? How are EM waves produced? How are EM waves produced?
They are produced.
Because we know how water waves are produced. We know how sound waves are produced. How on earth are EM waves produced? Because these things do not need particles. Do not need particles. So how on earth are they produced?
I feel like I've definitely learned this before. How are they produced? They have radio waves, microwaves, infrared. Oh, I don't know. Gosh, I forgot.
Don't worry, it is. It's not a particularly easy one unless you hear it every day, and nobody really hears these kind of things every day. So just a bit of a refresher will help you remember that you probably have heard it before. So this is an electromagnetic wave. So electromagnetic waves are composed of, let's just remind ourselves what they're composed of. They're composed of oscillating magnetic and electric fields at 90 degrees, 90 degrees to one another. Still hasn't addressed how they are produced. I'm simply stating the nature or oscillation of magnetic and electric fields at 90 degrees to one another. How are they produced is the key question. They are produced when charged particles are accelerated. Now, when I say accelerated, remember acceleration can be positive or negative. Negative acceleration simply means deceleration. So if you have the simplest way to produce a radio wave, for example, but a very dangerous way as well, Okay. Simplest way to produce a radio wave is to get simply a wire in your mains. Now your mains have got alternating current, haven't they? Yeah, like I
Yeah.
said, very dangerous. This is definitely nothing to be tried or, off the record, not to be done at home under any circumstances. All right. So if I've got a wire and I plug it into my mains, what's going to happen in here is now these electrons in my wire are going to be oscillating, aren't they? Going up and down.
Yeah.
Due to this current. Now they're accelerating because for them to slow down and then come back to where they came from, there is a deceleration and an acceleration. This here becomes a radio antenna and you produce radio waves. So anytime you've got charged particles which are accelerated, you get EM waves. Another thing as well is, but you will learn this later on, which is to do with electron energy transition levels in an atom. When an electron leaves, now of course you did chemistry, GCSE. So when an electron leaves a higher orbit shell and goes to a lower one, it releases a photon of light. That's another way in which EM waves are produced. So far, so good. So key thing to note is that we have, like I said, these fields. This is always a bit tricky to draw, but I'll do my best. Let's try this. And we are going to have our another field there, like so. Kind of get the idea.
Yeah.
Right. All right, there we go. And of course, the gray is here. Oops. And they are 90 degrees. So you've seen a diagram like this. Yeah, certainly you've probably seen a diagram like this. So one of them is an E field, and the other is a B field or a magnetic field. In physics, we normally use the letter B to represent or denote the magnetic field. These two fields are what we say they are in phase with one another. So the peak of my E field corresponds with the peak of my B field. This is just one transverse wave. Now I'm going to ask you a question here because, so I've only drawn one EM wave here. There's not many in different planes. So now I'm going to ask you, in terms of the plane of polarization, would you say, I know it's very difficult to look at this, but would you say this is horizontally polarized or vertically polarized? So remember that the blue here now, so if you had your eye looking here, because my diagram was not that great, so if you're looking directly, what you would see is you would see the blue doing this, and you would see this B field doing that.
Yeah.
So this is if you looked at the end on. So now I've drawn it for you so you can have a bit of a visualization. Would you say that this is vertically polarized or horizontally polarized, this wave I've drawn here?
For the E field.
Would you say that is
thing?
for the whole thing? So let's
Um,
imagine this is a light wave. Let's call this a light wave. Oops, let's use a different color. So we're calling this a light wave. So just like the light you'd be looking at through your lamp or from the sun. Well, okay, if it was from the sun, we know that it would have lots of different, but let's just imagine that there you go. You have one light wave of this nature and it has been polarized. That's the only reason. That's the only way you can get one produced. Would you say it is vertical or would you say it is horizontal? The polarization.
I'll go this vertical.
Vertical? Why not horizontal?
Because it's not horizontal. The light wave isn't.
Even though your eyes won't be able to see that. Now, that's a very difficult question to actually address in terms of answering, actually. But you've tried, and you made the right guess. It's vertically polarized. So when we talk about light or EM waves, the plane of polarization is dictated by the plane in which the E field is, not the B field.
Yeah.
Good, excellent. So E field, we're going to put a little note here. So E field determines plane of polarization. So this here is vertically, sorry, that's your E field. So light source is vertically polarized. Good. Now, let's go on and just think about then what happens if you have, let's move away from this here. Sorry, something is just gone a little bit slow. Let me insert page, blank page before current. Good. Okay. So now we have, let's imagine, I'm just going to be concerned with the E field here now, Conrad, yeah, because we know that that's the one that determines the plane. So let's imagine we've got unpolarized light and we're looking at kind of end on, just as we did in this instance here. Or are we? The first instance here, we're looking at it end on. I'm not going to be drawing these 3D dimension type of stuff. So here we go, and this is just E fields unpolarized E fields. And I pass this through, let's just imagine that, I pass this through a Polaroid that is, if you like, vertically aligned. How are these things made, these Polaroids, anyway?
I know it's very different to the diagram.
Yeah.
But if we were to draw it, if it was vertical, you'd just do vertical lines going down.
You just draw vertical lines, you're right. And what they do essentially is, you've got, do you do chemistry at A level by any chance, Conrad?
No,
that's okay. So what subjects are you doing again, Conrad? Are you doing physics and?
Philosophy, English and art, so it's quite a wide range.
That is a mix and a half. That you're
yeah,
definitely
it's
exercising the left side of your brain. Yeah, the right hand side of your brain. Brilliant, good combination. That's very good. So you've got a lot of connections you can make when I'm talking about these things, which is good. It's literally just formed by elongating or stretching molecules. These molecules can stretch, so you can stretch them, vertically. So you're right. If I drew this here, this is really just representing that these molecules now have spaces, but they are in a vertical plane. Yes, this would mean all these other orientations will be omitted once this light passes through my Polaroid. So on the other side, all I'll have emerging is just a single plane. If I took another Polaroid, and this Polaroid was also aligned in the same plane, then what would I expect to see of my intensity? So let's just have a little bit of a diagram here where we are going to draw intensity. Oops. Now I've used the word, and anytime I use a word, I like to make sure that you know what it means. What does intensity mean?
It's sort of the strength. Can you say how much of something that is? That's
Nearly
like
there.
not very. There's not really a scientific way to.
Yeah, no, I understand what you're saying, and but you've kind of got the general idea, because we use the word, oh, that was intense, or so there's a general idea instead of you in terms of from using it from everyday usage. But of course, when you come into the realm of physics, it then carries a very specific meaning, and by intensity we mean it is the power per unit area. And to help us remember what it is, it's worth remembering what the units are. Because if you can't remember the definition, but you can remember the units, chances are you'll remember the formula. So what do you reckon the units are for intensity?
PA to the -1. Is that
PM to the -1?
So power over area. So that would be P times A to the -1.
Nearly. So let's just think about what are the units for area in physics generally?
Oh gosh, yeah. Sorry, I don't know why even. Meters squared.
Very good. So and what are the units for power?
Watts.
Correct.
So WA to the, I don't know why I said the.
No, it's okay. It's been a long day, and it's been a long week for me as well.
It has, yeah.
WM to the -2. What's per
Yeah.
meter square? So if I plotted on my graph now, say the angle of rotation. So this is angle of rotation. And this, we're going to go from 0, and we might have 90, 180, 270, oops, 360 in degrees. So at 0 degrees, so this is my 0 degrees orientation. So let's imagine we're going to be rotating it this way. So at 0 degrees, I've got maximum intensity, isn't it?
Yeah.
As I start rotating this through 90 degrees, what are you going to expect is going to happen when this is now at 90 degrees?
The intensity, if it's at 90 degrees.
Yeah, so if I rotated this, spun it through 90 degrees, what would the intensity be?
0.
You're right, because by the way, the observer, I am this side. That's us. So we're looking on that side of things. So 0 at 90 degrees. Cool.
Yeah.
Very good. What about at 180?
Back to
winning ways, isn't it?
much, yeah.
So max. So these are my max values, by the way. Okay. And then if I take it through 270?
0.
0 again. So now I have a profile that looks something like this. Okay, remember ever seeing a little pattern like that?
Yeah.
Excellent.
Yeah.
Excellent. So this is worth remembering, that particular pattern, because sometimes they like asking questions to say, if you rotate it through these different angles, what will this look like? Now for the crux that a lot of teachers do not know about, but it's worth knowing about because I have seen these questions asked in an OCR paper. So it's worth just knowing how to respond to this and respond to it correctly. So if I insert a page, blank page before current. If we have microwaves generally are already plane polarized. Okay, so microwaves, I'll put a note here, and we're going to say microwaves artificially produced, because you can produce microwaves can also be naturally produced. Yeah, so microwaves artificially, so the ones that are naturally produced are unpolarized, but the ones that we produce ourselves are generally so microwaves artificially produced are polarized. This means if I have a transmitter and inside it is a vertical transmitter, let's just say that's my vertical transmitter. So this is transmitter. Vertically polarized. And I take, so my waves are coming out in a vertical plane, my microwaves, vertical. And I take a receiver. It's my receiver. And my receiver is also, needs to have an antenna that is also vertical antenna. This here is my receiver. At this point, I've got maximum intensity. If I rotate my receiver through 90 degrees, oh, that's not. If I rotate my receiver through 90 degrees, what's going to happen to my signal that I receive on my receiver?
It will go to 0.
Correct. It'll go to 0. Spot on. Now this is where it gets into the spooky side of things. Okay. Okay. Now let's imagine I'm going to ask you here. Now I get a metal grill. Yeah, I get a metal grill. And this metal grill, I'm going to try and draw this as best as I can. Let's use gray for metal. There's my grill. And my grill is vertical. I didn't want this yellow part.
Oh, don't worry.
My metal grill is vertical. And my receiver antenna is also vertical. My transmitter is also vertical. The question is now, Conrad, will my receiver show any signal? So my grills are vertical, my waves are also vertical, and my receiver is also vertical.
Seeing as this is a widely misunderstood question, I'm not going to go with the obvious answer.
Good. Obvious, you're right. You're not going to drop into the same trap. Very good. I like that. Yeah. So you will receive no signal. 90% of physics teachers will tell you there's going to be a signal. And you can see why they would think so. Because all the examples we've looked at is if this is vertical, everything should, Now I rotate this through 90 degrees. Yeah, so the scenario now is that this is horizontal, the grills are horizontal, but the waves are still vertical. Guess what will happen to the signal I'll now receive?
Will it go back up?
It will be maximum. Hey, what's just happened?
Yeah, what has just happened?
I know. How do you reckon we might be able to explain that?
I guess if always. I don't know.
Yeah, the way to think about this, and like I say, it's really, really interesting, but worth remembering because I've seen a few of these crop up. Because this is vertically aligned, when these microwaves hit, remember this here is, by the way, I mentioned it's a metal grill.
Yeah.
Metal, because this is now at maximum intensity, these are vertical, this metal will, or the grill itself, will absorb the microwaves. And that energy from the microwaves will be used to increase the temperature of this grill. Furthermore, because this metal grill has got electrons inside, they also will then produce microwaves, but these microwaves will be scattered off in all directions, and very little arrives at the receiver. Very counterintuitive. When you rotate it, however, through 90 degrees so that now it's not aligned with the plane, these metal grills now cannot absorb as much energy from the microwaves. So majority of the microwaves now pass through. So please note here that there is an exception to polarization, how we deal with polarization if we're dealing with microwaves and a metal grill. All right, that's the key thing I want you to know. Brilliant. So you've got that. Excellent.
Yeah.
Now, let's just think about, so those are the main key aspects of polarization. So what we've been looking at here, by the way, when we looked at this filter, this was full polarization. When we looked, oh, where's it gone? Where is it disappeared to? Oh dear. I think I went a bit too far here. Have I just lost the page?
I don't, I've written, oh, maybe you have.
I've lost the page.
The intensity one. I've written,
how on earth did that happen? Oh, it must be on, sorry, maybe it's on, I've never seen this happen like that. Sorry, it was on the other side. Right, okay, there we go. So this is a very different scenario. Now, this here was full polarization, but sometimes there's also something known as, let's insert a page here, blank page after current, partial polarization. When does partial polarization take place? Ever heard of partial polarization?
I don't think so. I don't know.
So if you have, it could be a lake, and you have your sun, and the light reflects off this lake. It could be a puddle, it could be anything. Yeah.
Yeah.
When it reflects, or upon reflection, the reflected wave will be partially polarized. So meaning there'll be a majority of waves that will be in one plane. You still have others in different planes, but majority of them will be in one given plane. So this is what we call partial polarization. Occurs when unpolarized light, e.g. from the sun, reflects off water. In addition to then understanding this key thing about polarization, the other thing that they might ask you here and there is just the uses of polarization. What are the practical applications of polarization? Anything that you can think of?
Sunglasses.
Correct.
Windscreens.
Sunglasses, yeah. Windscreens.
Can you say with some types of? I guess those are all types of windows. I guess all types of some types of windows.
3D goggles.
Oh yeah, 3D
movies
goggles
are made.
Yeah, with the blue and red.
Yeah, so what they do is nearly there. So when you wear those 3D goggles you wear, one of the lenses is vertically polarized. The other is horizontally polarized.
So interesting.
Yeah, in 3D goggles. So one set of the movie is shot with horizontally polarized lenses and another with vertical. So what this then does is when you then look at it in your eye, it gives you the impression of looking at a 3D image. Because now you've got one plane of polarization aligned with another, which is what you see when you're looking at something in real life. Because the rays that are reaching your eyes are all polarized in different orientations. Yeah? So 3D goggles, another applications as well, things like stress analysis. So if you want to see which parts of machinery undergo a lot of stress, you would use Polaroids, and that is again another application. Stress analysis of materials, of we'll say, let's just say engineering materials, shall we? Engineering materials. Another one as well is to discover planets, discover exoplanets. Now, the way they do it is they look at the reflection of light from other stars, which has hit off, if you like, off lakes on other planets. Now, of course, if a planet has water, chances are there's life.
Yeah.
And that is part of the hunt to try and find if there is life out there. So that is another thing that is also used, another application in terms of polarization. Okay?
Yeah.
Super. That is all you need to know about polarization. You don't need to learn about Malu's law.
So what school do you teach at?
I teach at Clitheroe Royal Grammar School.
Might have to switch schools.
I'm not sure. What is that?
My teachers are lacking a bit.
Are they? but we're up in the Lake District. So
I actually
which
visited the
school you
Lake
at, Conrad?
District a few months ago. It was really nice.
Oh, good. Which school you at
Yeah.
then?
I'm at Alexandra Park School in London.
Okay.
It's literally a minute away from my house.
That is a bit
So
ideal though.
next to the lake. Yeah, it is.
That is ideal
Um,
for London. Like you just miss
yeah,
all the commute and all that.
exactly. Yeah,
Yeah. I
yeah.
lived in London for a long time, and I've got family and stuff in London. So
That's really nice.
I do come to London every now and again, but
Yeah.
I don't miss the hustle and bustle so much. It's very quiet out here, lots of
Yeah,
fresh air,
I've been
lakes.
lucky to live close. Yeah.
Yeah. But
It's really nice.
I'm glad that you've now got a nice gist of polarization. Yeah. In the
Yeah.
next lesson, we are going to go into the deep end of things. So this was not quite the deep end of things. So when we start getting into double slits, which is what we're going to do next lesson, and diffraction gratings, we will definitely be delving into more calculation type of things. This wasn't too calculation intensive. But what I'm going to do, just to keep you a little bit busy until we next meet, I will include some questions here for you to have a go at, and have a go at in your own time. I will include the answers, and then you can have a go looking at the answers and seeing how well you get on with those, and then we shall pick up pieces on Young's double slit.
Yeah.
Super.
Also, how many lessons do I have left? Because I'm going to book some more. How should we pay you for the new lessons?
Okay. Well, in terms of, that's a good question. So you'd have booked a block of 5, didn't you? You booked a block of 5. So we've had, is this our third one?
I can actually probably check in my book.
I'll check for you. That I can check. I can check in my email, because I send you work anyway, so I can tell exactly how many I've sent. Okay, so I'll tell you exactly how many lessons we've had, Conrad. I think it's about 3.
3.
1, 2, 3.
I think I can check on here.
Yeah, you can check there as well. Have a look there. 1. So you did that one.
It's our 4th, I think.
4, right? Okay, so it's 4 now. You've got the number right. Yeah. Today makes the 4th, doesn't it?
Yeah.
All right, cool. All right, super stuff. No worries. It's all good.
Yeah, I mean, if you just email me with all the details, I can just.
You can get that moving on your side.
On email, yeah.
Sweet. Okay, cool.
Brilliant.
Do you have any questions over what we've done today, Conrad?
No, so far, I mean, I've really got a much better understanding.
Yeah, good.
Definitely. No, I think
just for the fun of it, on Monday, can you please go and ask about one of your teachers about the microwave with the grill?
Yeah, I will.
Just to make heads spin in the department. Well. Okay. And please let me know what kind of worms you open up when you do ask them that.
Oh, that'll be funny.
Super, good stuff. Right, so I'll see you on Friday, and you have a great weekend,
Have
Conrad.
a great weekend. Thank you so much.
Nice, and see you soon. Yeah.
See ya. Bye.
Bye now. Cheers. Ta.